Hi everyone, welcome back. Today we're going to be looking at how to calculate arc length and sector area. Just going over some vocab words first, starting with what an arc is. An arc is a part of the circumference of a circle. And remember, the circumference is actually the outside of the circle. And that arc is subtended, aka like made up of the central angle here. So if we were to label that on our little graph over here, this part of it would be considered an arc. Basically the outside length is an arc. This is an arc. And then other new word, a sector, is a slice of a circle that's bounded by an arc in the two rays of the central angle. So the sector is actually the inside part. It's kind of like a slice of cake if you think about it. This part right here would be the sector. And because it's a three-dimensional space, or excuse me, a two-dimensional space, that's why we can find the area of it. And notice it says it's bounded by the arc and the two rays that come out of that central angle here. So we do have a little formula to calculate arc length. We use the letter L for arc length. Okay, so we have theta on the top out of 360, and then we multiply that by 2 pi r. So the theta itself, this right here, is actually the central angle. Central angle. And then the part that we're multiplying it by, this 2 pi r, if you remember from geometry, that's actually the formula for circumference of a circle. So what we're actually trying to find with this formula is basically we're doing a fraction out of the entire circle. So a fraction of the circumference. And that's how we'll get that arc length. Basically, it's just a part of the entire circumference. Looking at the first question, it says find the length of each arc, leave your answer in terms of pi. Now what I mean by leave your answer in terms of pi, that means you don't want to grab your calculator and type in 3.14 or even use the pi button. You almost treat the pi like it's a little variable. So looking at the first question we're given, the radius is 10 inches and the central angle measures 45 degrees. So in our formula, if radius is 10 inches, this should be our r variable, and the central angle of 45 degrees would be our theta, which is that theta out of 360. So I'm going to take those two and substitute them into my arc length formula. So I'll have arc length equals my theta out of 360, which would be 45 out of 360, times 2 pi, and then multiply by my radius, which is 10. And then we're going to slowly get this simplified. Now when we simplify this, again, remember, don't grab your calculator and type in 3.14. First thing I want to do is reduce this fraction here. 45 out of 360 actually does reduce quite nicely. Both of these numbers divide by 45. 45 divided by 45 is 1. 360 divided by 45 is 8. And then if I multiply my 2 times my pi times my 20, I'll have 1 over 8 times, this would become 20 pi if we're leaving it in terms of pi. And then you kind of have an option here. You can multiply first and then reduce. You can also multiply diagonally. I'm going to go ahead and just multiply top times top, giving me 20 pi, and bottom times bottom, giving me 8. And then I'm going to reduce both the 20 and the 8. Both of these divide by 4. That would give me a 5. That would give me a 2. So the final answer for my arc length in terms of pi is 5 pi over 2. And these were measured in inches. And since it's just a measure of length, it's not a measure of area, we would just label it with inches. And then similar for the second one. The second one, though, we are given that the diameter is 36. If you remember back from geometry, the diameter is the distance all the way across a circle, so that would be this. So if our diameter is 36, that actually means our radius is 36 divided by 2, which would be 18. And then again, my central angle here, which is theta in my formula. So my central angle, I'll label there. We'll substitute those two into our arc length formula, which remember is L equals theta out of 360, so that's 160 out of 360, times 2 times pi times my radius of 18. Again, just like the last time, I'm actually going to reduce this little fraction first. Both of these divide by, I believe, 40. 160 divided by 40 would be 4. And then 360 divided by 40 would be 9. And then we can also simplify this 2 pi times 18. So I would have 4/9 times 2 times pi times 18 would become 36 pi. Okay, and again, remember, you cannot just, you can not only simplify within the fraction itself, you can also simplify diagonally first. I'm actually going to do that on this one just to kind of show you a different way. Both 36 and 9 are a factor of 9, or a multiple of 9, excuse me, so we can factor out 9 from both, divide this one by 9, and then it kind of just becomes mental math. We've got a 4 times 4 pi on the top. 4 times 4 pi would be 16 pi. And we've got a 1 times 1 on the bottom, which would just be 1. So the final answer for my arc length is 16 pi. Sorry about my screen going dark. Okay, looking at the next one, it says if the length of the arc of a circle with a radius of 8 centimeters is 8 pi over 9 centimeters, what is the measure of its central angle? So the length of the arc is 8 pi over 9. We're trying to find its central angle, and we also know that its radius is 8. So if we're trying to solve for the measure of the central angle, that means we're actually solving for the theta in our formula. Solve for theta. Oh, adjust camera, excuse me. One more try. This is an old camera at home. Okay, I guess we'll adjust the paper instead of adjusting the camera. Okay, so we are solving for theta. Okay, I'm going to start by just writing my formula. My formula, remember, is arc length equals theta out of 360 times the circumference, which is 2 pi r. And then I'm going to fill in what I know. I know the radius is 8. Pi is just a number, so we're not going to we're not going to change that. The theta is what we don't know. That's technically our variable. And then the arc length is actually what we are told. The length of the arc of this circle is 8 pi over 9. So I'm going to fill that in for my arc length. And then we're going to work on getting this solved. Let's see. First thing, I'm actually just going to kind of simplify what's on the right first. If I multiply everything that's on top here, theta times 2 times pi times 8, I would basically get 16 pi theta, where theta is my variable. And then if I multiply on the bottom, 360 times 1, that's just 360. And then I'm going to bring down the right side, that's 8 pi over 9. Okay, now looking at what we have now, we're trying again to solve for theta here. So I'm actually going to start by getting rid of the denominator by multiplying by 360 on both sides. So we're going to cancel the 360 on the right. On this left side, you can actually simplify these two. Both of them divide by 9. Obviously, 9 divided by 9 is just 1. But then 360 divided by 9 would be 40. And then I'm going to move my work up here. So now on this side, I have 40 times 8 times pi. 40 times 8 would be 320. So on the left side, we have 320 pi. And then on the right side, we've got, let's see, 16 pi times theta. 16 pi times theta. And again, our goal is to solve for theta, which is that central angle. So next thing I'm going to do, since both of these are being multiplied, I can actually divide by them at the exact same time. Divide by 16 pi on both sides, which will cross them out from the right and leave us with just theta equals. On the left side, the pi over pi will cancel. And then we really just need to do 320 divided by 16, which 32 divided by 16 is 2. So 320 divided by 16 would be 20. 20 degrees is the measure of the central angle. All right, little application. This application actually comes from AP Classroom. It says 2 satellites are orbiting the Earth. EarthSat is the name of the first one. It has a circular orbit with a radius of 175 kilometers. And it sweeps out at an angle of 540 over pi. The second satellite, Moonsat, also has a circular orbit, which kind of is just telling us like we're dealing with a circle here. It also has a circular orbit with a radius of 160 kilometers, and it sweeps out at an angle of 720 over pi in the same span of time. So the question is, which satellite traveled a greater distance in that span of time? So what we're actually thinking about if we're on a circular orbit and we're swinging out at a certain angle using a certain radius, that actually means we're comparing the arc lengths of both of these circular orbits. So what we're trying to find is which has a greater arc length. Which has a greater arc length. Okay, so we have to break this down. We've got 2 different ones. We have EarthSat, and we have, what was the other one? Moonsat. I assume SAT stands for satellite. Moonsat. Okay, so I'm going to start by calculating the arc length for EarthSat, excuse me. Again, our formula is theta out of 360 times 2 pi r. So we're going to have arc length equals, our central angle is 540 over pi. So we're going to have 540 over pi out of 360. So this is my theta right here, times 2 pi times my radius, which the radius for EarthSat was 175 kilometers. And then we are working towards getting this simplified for our arc length. Let's see, right here we've got a fraction divided by 360. Remember, dividing fractions, you can actually take that 540 over pi and multiply by the reciprocal of 360, would basically be multiplying by 1 over 360. And then I'm going to also bring down my times 2 pi times 175. So we kind of just have a big pile of multiplication here that we need to simplify. Let's see. Remember, you can simplify not only like vertically within the same fraction, but you can also simplify diagonally, and that includes diagonally here. So I'm actually going to cross out those pi's because they cancel out. Cross out, cross out. So if you look at what we have left, on the top we have a 540 times 1, feel free to write it, times a 2, times a 175, and on the bottom we just have a 360. So I'm going to take this now and pop this into my calculator instead of trying to simplify by hand, just for the sake of time. Let's see, we'll have 540 times 2 times 1 times 2, excuse me, times 175. And then all that's going to get divided by 360, which is 525. That actually multiplied out beautifully. So the distance that EarthSat traveled on that arc was 575, excuse me, 525, what did it say? Yes, 525, what are these measured in? Kilometers, kilometers. So there's the first answer. And again, we're trying to figure out which one had a greater arc length. So I also need to do the same calculation for the Moon satellite. So using the same formula, arc length equals my central angle, which is 720 over pi, out of 360 degrees, times the circumference, which is 2 pi times my radius of 160. And then again, I'm going to do the same kind of simplifying on this one. 720 over pi divided by 360 would turn into 720 over pi times the reciprocal of 360, which is 1 over 360. And then I'm going to also bring down my 2 pi times 160. Let's see. Obviously, your pi's can cancel just like we did on the last one. If you want to, you can do a little bit more simplifying, but I'm actually just going to go ahead and bring mine down so I can multiply. This one is moonset. Let's see. On the top, we'll have 720 times 1 times 2 times 160. And on the bottom, we have 360 times 1, which is just 360. I'm going to grab my calculator and see what that comes out to. Let's see. 720 times 1 times 2 times 160. And then we're going to divide that by 360. So the distance that Moonset traveled on its arc length was 640 kilometers. So then to answer the question, which satellite traveled the greater distance in that span of time, the Moonsat is greater. On the back side, we're going to take a look at how to calculate the area of a sector of a circle. It is actually a very similar formula to the one that we just used. It's just instead of having the circumference formula, you would then use the arc length formula. Oh, excuse me, instead of having the circumference here, you would use area of a circle here. So our sector area, it looks very similar, except right here on the previous side we had circumference, but on this one we actually have the area of a circle formula. It's still theta out of 360 because you're still taking a fraction of the entire circle. It's just you're swapping it out and having area of a circle right here. Theta is still our central angle. Looking at the first questions, it says to find the area of each sector and then leave our answer in terms of pi, which again, members, we don't want to grab our calculator and type in 3.14. We just want to leave that pi there, almost like a little variable. So the first one, the radius is 14. Our central angle is 135 degrees. So the sector area would be our central angle, 135 out of 360, times area of a circle, which is pi times the radius squared. And then we're slowly working on getting this simplified. 135 out of 360 actually reduces, both of these reduce to 3/8. Okay. And then 14 squared is 196. So this is 3/8 times pi times 196. So when we simplify this, I'm actually going to start by multiplying everything on the top together. 3 times 196 is 588. So on the top we'll have 588 pi. And then on the bottom, 8 times 1 is just 8. And that can reduce just a little bit more. Both of these numbers are divisible by 4. 8 divided by 4 would become a 2. And then 588 divided by 4 would become 147. So the final answer for the sector area on this one is 147 pi over 2. And since this is a measure of area on this one, unlike the arc length where we just labeled it inches, area will go with squared inches. Second one is similar to the one we had on the front. We're given diameter instead of the radius. So if the diameter is 54, the radius is half of that, meaning our radius is 27. And then we have our central angle, which remember is theta. So setting up our sector area formula, we'll have S equals theta out of 360 times pi times the radius squared, because remember that's just area of a circle. And then I'm going to start simplifying and reducing. 75 over 360 does reduce. That reduces to 5 over 24. 27 squared is also 729, I believe. Double checking. 27 squared. Yes, it's 729. So we'll have 5 over 24 here times pi. 27 squared became 729. And then I'm going to multiply all the tops together. 5 times pi times 729 would become 3,645 pi. And if I multiply the bottom times bottom, I'll get a 24. And then I do believe this reduces. When you reduce, I kind of just ignore the pi on it. 3,645 divided by 24. I'm going to do a little math one. It does reduce. 1215 over 8. 1215 over 8. So our final answer for the area of the sector would be 1215 pi over 8. And remember to include the squared units, so we would say meters squared. Okay, we have one where we're kind of working backwards in the next section. It says, if the area of a sector of a circle with a central angle of 120 is 27 pi centimeters squared, what is the measure of its radius? Okay, so we are solving for radius on this one. I'm going to start again just by writing my formula. Sector area equals central angle out of 360 times pi r squared. Okay, so we know the sector area already. I actually know this is the area, and I specifically know that because they use centimeters squared as the unit, and that is a area measurement. So we'll say 27 pi equals, our central angle out of 360 would be 120 out of 360 times pi, and then radius is what we're solving for, so pi r squared. Let's see what we can do. One thing we can do, 120 over 360 actually reduces quite nicely. That reduces to just 1/3. So I'm still going to have 27 pi on the left, but on the right side, if I multiply all the tops together, 1 times pi times r squared, that's pi r squared. And if I multiply the bottoms, 3 times 1 becomes 3. And then from here I can solve it. It looks pretty normal to solve it now. I'm going to multiply by 3 to cancel my denominator. That leaves me with, on the left side, that would become 81 pi. And on the right side, I have pi r squared, which you can kind of see the answer forming already. If you divide both sides by pi, both of those pi's will disappear. And we're left with 81 equals r squared, which means when you take the square root, the radius is 9. Now remember, you don't have to write plus or minus 9 on this one because this is a measurement, and we only want to write it the primary root, the 9. We can include a unit though, since centimeters squared was the area, centimeters would just be the radius. And then one last practice question. This one comes from AP Classroom. Grab my highlighter so we can annotate. It says Ferris wheels are common tourist attractions that consist of a rotating upright wheel with multiple passenger cars. Autofocus. Two famous Ferris wheels are the Singapore Flyer and the London Eye. I've seen the London Eye in person. I have not seen the Singapore Flyer. So we have some different measurements on them: height, the diameter, height, diameter. Suppose that a rider travels 100 meters along the curved path around each Ferris wheel. Which Ferris wheel will the rider swing out at a larger angle of rotation, and what is that angle? And we might need to round to the tens place. So it says the rider the rider travels 100 meters along the curved path. That's telling us an arc length if it's 100 meters along the curved path. So I'm going to go ahead and remind myself this is an arc length. Okay. And it says which rider will swing out at a larger angle of rotation. the angle of rotation is simply just that central angle. So we're actually solving for theta on these. Solve for theta. And so this question has nothing to do with sector area. It will be using the arc length formula. Excuse me. Sorry. Hey, put it out. Okay, so we're going to need to do a calculation for the Singapore Flyer. Singapore Flyer. I don't know if that's how you spell flyer. And then also for the London Eye. Olivia. Okay, so I'm going to go ahead and write down my arc length formula on both of these. Remember, arc length is theta out of 360, your central angle, Olivia, out of 360, times the circumference formula, which is 2 pi r. So theta, arc length equals theta out of 360 times circumference times circumference. All right, I'm going to start filling in what I know. For both of them, I actually know the arc length is 100. That's how much they traveled around the curved path. So I'm going to go ahead and fill that in for L on both. Okay. We don't know the central angle for either of them, so I'm just going to bring down that theta out of 360. Theta out of 360. And then for the Singapore Flyer, if its diameter is 150, then that means its radius is half of that. So its radius would be 75. So we'll say 2 pi times 75. And then for the London Eye, its diameter was 120, which means that its radius would be half of that at 60. So notice we did have some extraneous information on this one. We did not end up needing the height on either of these. So I'm going to go ahead and start calculating, and notice this question also does not mention to leave your answer in terms of pi, which means we are going to actually either use 3.14 or use the pi button on our calculator, which is second and then the up arrow right here. All right, so solving on the first one, let me see. If I just multiply these two fractions together on the right-hand side, theta times 2 times pi times 75, that would be 150 pi theta. And then on the bottom I have 360 equals 100. I'm going to multiply by 360 on both sides. 360 gets canceled here. So on the left-hand side, I'll be left with 36,000. And on this side, I'm going to bring down my 150 pi theta. Okay, so again, since we don't have to leave our answer in terms of pi, I'm going to go ahead and divide by 150 pi here, divide by 150 pi here, and then we'll grab our calculator to do that calculation to get a nice decimal. 36,000 divided by 150 pi, and they did say to round your answer to the tenths place, so on this one it would be 76.4 to the tenths place. Sorry about my computer falling asleep. 76.4 degrees for that central angle that this one rotates out. And then I'm going to do the same thing for the one on the right to see which one is larger. Let's see, if I multiply the two numerators together here, that would become 120 pi theta, which is what we're solving for, over 360 times 1, which is 360. Same as the last one, we're going to multiply by that 360, giving us 36,000 equals 120 pi theta. And then we'll divide by the 120 pi. And then again, not leaving it in terms of pi means we can actually use the pi button on our calculator. 36,000 divided by 120 pi. And this one, again, rounded to the tens place, we'd have 95.5 degrees. So then to answer their question, which Ferris wheel will the rider swing out at a larger angle of rotation? That would be the London Eye is larger. All right, guys. Thanks everyone for watching.